you have Carlsbad, New Mexico, which is kind of the other end member of a hypogene cave, which formed very differently than Mammoth Cave. And that was really quite new science a while ago. But they found out that through a lot of work by a lot of people, Carlsbad caverns actually formed from the bottom up in a way that we call hypogene, where you actually had rising acidic fluid and acidic gases that ate away at the limestone, again, from a different direction. And they were different kind of solutions as well. But we'll get back to that later because it sucks. So for now, I want to reorient people to Indiana, although we're all Indiana cavers. I just gave this talk in Portland and they're not Indiana cavers. And as you all know, Indiana is a place of historic karst study, and people have been doing just this here for a very long time. It's a proud tradition. This is Robert Judah's illustration of an idealized Indiana cave as presented in Dick Powell's Caves of Indiana book, which, by the way, if you haven't seen it already, the Indiana Geological and Water Survey just re-released Dick Powell's book on their website. It now has the cave maps that are private and not gated redacted, and all the locations are redacted, but there's a lot of good historic information in there. And so we wanted to make that available to people. And it also includes a memoir from Dick Powell in the beginning of it. That's, again, open access. It's freely available. Just Google it, you'll find it. So of these incredible scientific studies, there was a really important person who did work here, and that was Art Palmer, and some of you might know him. And he actually did his PhD at Indiana University, where I did my master's. And Art Palmer did work in Blue Spring Caverns, and actually I heard someone here today say that it was the last cave they went to, so they have it fresh in their mind. But Art Palmer mapped Blue Spring Caverns with his now wife, Peggy. And at the time, it was the longest, or it was the, what was it, 6th longest cave in the world at 18 miles, which is no longer true at all, but it really speaks to how cutting edge this work was. And what he said about it was that it was a floodwater diversion maze cave. And so it was forming by the back flooding from the East Fork of the White River and the flooding of the cave through that meteoric rainwater flushing through the conduits. And then there would be collapses as the sinkhole plane overhead would shunt rocks down, and that would cause a new conduit to have to form. And it's how it got so convoluted. And you can see this is just the topography over the cave, and you can see how pitted out it really is. Oh, we're tilted. I didn't even notice.
Just did it by itself.
Sorry, for folks on the internet, the projector has moved, and so we've got a moving target behind me, but that's all right. I'll just keep talking. So anyways, Blue Spring Caverns, sinkhole plain. This is also the Mitchell Plateau, going through the flag over there, down towards the floor. And the area of study I kind of marked there in yellow. So that was Art Palmer. Now I have a projector in my eye. That was Art Palmer. And he did really foundational work on looking at how epigenetic caves form. And his work is cited all over the world. He still does it. Everybody loves him. There was also someone else here at IU named Noel Crothy, who did a lot of really quantitative geochemical work. Art Palmer looked at the ways caves were forming based off of the morphology of the cave, the morphology of the landscape, and the way that water was moving through that. And he used that information to figure out how the cave got there. What Noel Crothy and the people he worked with did was they looked at the chemistry of the water to figure out the way that the water was moving and make an argument about not how the water got there, but how the water was actually working in the system and how the water was mixing. And so this on the left side of the screen is a pipe, we call it a Piper diagram, but it's showing different water chemistries of different springs that Noel Crothy sampled in Indiana. And it's not important to get into the weeds, but it is important to notice that there's a lot of different chemistries, and there are a lot of different bubbles he has drawn in, showing that the water isn't all the same, and that means it's not all coming from the same place. And I really want to draw your attention to this axis of the diamond here, where sulfate is increasing and nothing else is really changing. And that's going to be really important for the rest of the talk. And he thought it was important too, because on the right side, he looked at that sulfur relationship, and he looked at on the y-axis there is the concentration of sulfur, and on the x-axis is the ratio of heavy sulfur versus light sulfur, or the isotopic ratio. And I'll talk about that more. And again, it's not important to get into the weeds about it. Oh, wonderful. Thank you. I appreciate it. Great. It's not important to get into the weeds about it. But what is important is that there's a relationship between the type of spray, the type of sulfur, and how much sulfur. And so as you get this heavier sulfur, you have more sulfur, and it's coming from diffuse flow. Whereas when there's lighter sulfur, there's less sulfur, and it's coming from conduits. And he took that and worked with it for decades, just like Art Palmer worked with his cave arguments for decades. And he saw at Orangeville Rise, and Orangeville Rise is one of the terminal outlets for the Lost River, which, for folks who don't know, is the longest sinking stream in the state of Indiana. And it has a 20-some mile cave in it. And Orangeville Rise doesn't take water directly from Lost River. It takes drainage from the section north of it, but it goes into the Lost River dry bed, so it's all very confusing. But the point is, it is a mixed geochemical system. So what Noel Crothy did was he took these sulfur isotopes, and he took water samples during a rain event, and he looked at the type of sulfur it was and how much sulfur there was. And he was able to create a crazy mathematical linear algebra mixing model to show how much water was coming out of different parts of the rock at different times based off of the sulfur content. And so the point I'm getting at is that Art Palmer took geomorphological and hydrologic evidence to make a speleogenetic argument about how caves formed in the area. Noel Crothy took geochemical evidence to make a hydrologic argument. What I'm going to do in this talk is take geochemical evidence to make a speleogenetic argument. And what we see is that the results are not the same as what the other people here who did fine, great work for decades found. Because when you look at things a different way, you see different things. And so this is where people's eyes glaze over and everyone goes to sleep, and that's okay. But this is back to what I was talking about before. This is that mammoth cave type cave formation pathway. And this is that Carlsbad Caverns type cave formation pathway. The important thing to notice, number one, is that there's a different acid involved, because to make a cave, you have to get rid of rock. And to get rid of limestone, we dissolve it. And so here we have carbonic acid forming based off of the reaction between CO2 and water. So CO2 from the air is dissolving in water, which happens in rain. And that is a weak acid that can dissolve limestone. And that happens from the top down as rain percolates down, and as plants respirate, they breathe the CO2 out into the soil and it makes it more acidic. In sulfuric acid speleogenesis, which is generally hypogene, you have hydrogen sulfide that has to come from some sort of, we call it reduced source, so some sort of oil or something else. And it's, or it could be anything. It could be coal, but it has to be deeper. It has to be away from oxygen. And then as that reacts with oxygen, it forms sulfuric acid. And that is super caustic, and it dissolves limestone way faster than carbonic acid. So anyways, don't think about it if you don't want to, but I took water samples all over the Mitchell Plateau, actually just at 4 places, 2 times a month for 2 years. And I took them at Blue Spring Caverns, Flood Creek, Wesley Chapel Gulf, and Orangeville Rise. And mostly for this, we'll focus on Blue Spring Caverns. But we also had a rain gauge station. That's someone from work being very friendly. This is just kind of the basic distribution of those water samples. And again, I'll draw your attention to sulfur is an important axis. And beyond that, you don't really have to worry about this diagram, but it's important to realize that each color is a different site, and that within the sites, there is variation. It's not all a little bubble. There's different things happening over the course of the year. And between the sites, there's variation. And that's related to the position of those sites in the watershed and the length of time that they're interacting with the rocks, because it changes the water chemistry. And so, again, don't worry about the numbers, but it's important to look at these things. And a lot of what we do as scientists is just look for patterns and then see how we can explain it. And so this is the full data set that I have for specific conductivity, which we just use as a proxy to understand how much of stuff is in the water. How conductive it is related to how much dissolved content there is. And so here you can see that during dry season, how much stuff there is goes up. And Flood Creek is dry during dry season because it's a sinking stream, and these other sites are cave water directly. So that's how we define dry season, was when there was no water in Flood Creek, if you were wondering why that lined up so nicely. But interestingly, Blue Spring Caverns, which is here in blue, and Orangeville Rise, which is here in orange, are both the terminal. Well, Blue Spring Caverns isn't terminal, but it's close to the terminal sump. We couldn't sample the actual spring, but they're very close to the terminal resurgences of two karst watersheds, but they're different karst watersheds. And what you'll see is the amount of specific conductivity they have is higher than the other sites at any time of the year, but it actually trades off between the two. And we'll get back to that later. But when we look at the sulfur, we see a really crazy pattern at Orangeville Rise. And this was actually what Noel Crothy studied, was these high spikes during dry season. And so that wasn't unexpected. What was unexpected was the Blue Spring Caverns kind of did the same thing, whereas Wesley Chapel Gulf and Flood Creek stayed baseline throughout the year. At Orangeville Rise, we took this data and we transformed it based off of a relationship that Lee and Crothy found in 2003 that said that so much of the sulfur should be from diffuse flow at any given point in time. And what that means is that sulfur is coming from gypsum beds in the St. Louis limestone. And gypsum is calcium sulfate, and it's very soluble in water. So as you have rainwater going through the aquifer, sinking down, it dissolves that gypsum out and it takes it out into the spring. And so at Orangeville Rise, you can see that during dry season, almost all of the sulfur is coming from that gypsum, whereas during wet season, some of it is coming from something else, which is probably rainwater, because there's a little bit of sulfate in natural rainwater. And it doesn't line up perfectly, but that's probably because Noel Crothy's data set wasn't over the course of one rain event, and ours was over 2 years. That's all okay. And I would love to talk about that more, but we have more interesting things to talk about, which is sulfur isotopes. And so we start with just, this here is from Noel Crothy's study. And this is looking at Orangeville Rise water. And what you see immediately is that we basically reproduced this in our study, which is good because science should be reproducible. And this is an end member of St. Louis anhydrite. So that's the gypsum I was talking about. And what we see is that the sulfur content of the water is being drawn upwards as you have more. It's more like that gypsum signal, because that's one of the main sources of gypsum at that site. And that's great. But we noticed something else, which is Blue Spring Caverns seems to have nothing to do with that at all. And we did not expect that. We didn't even expect there to be elevated sulfur at Blue Spring Caverns, but it's doing something else. And that's when we found something super weird, which was petroleum seeps in Blue Spring Caverns. And this had not ever been described before in science, not in all of Art Palmer's work. And I didn't actually find them. It was the tour guides at Blue Spring Caverns who did, namely Nick Kaufman. So big thank you to him. Yeah, he's wonderful. And what happened was I was actually showing them that data set and saying how weird it was. And I was like, the only thing I can think of is this weird stuff I've seen down in Kentucky, which I'll show slides of later. But there's nothing like that here. And Nick goes, yeah, there is. And I said, really? And then AJ, who was also there, was like, no, man, that's poop. That's not anything. And Nick was like, no, it's petroleum, I swear. And they had a fight about it. And I said, well, I can fix this. Just take me there. And it was not poop. It was petroleum. And so I got a thesis. And what is actually going on here, apparently, is that you have petroleum coming out of the cave floor, and this is a bedrock fracture, and it's migrating along these fractures, and it has hydrogen sulfide. So that white haze is bacteria that's eating that reduced sulfur that's coming out of the petroleum, and it's converting it to sulfate. So that sulfur appears to be coming from the breakage between the carbon sulfur bonds, because those are weaker than the carbon carbon bonds in the petroleum, and so it comes off faster as the bacteria eat it. And then that H2S is released, bacteria mediate its oxidation, and the sulfate comes down to the cave stream where I was sampling it for 2 years without even really realizing it. And I took a sample, and it's actually pretty complicated, because if you expose hydrogen sulfide to the air, it's very volatile and it goes away. So to take a sample of this, I had a bottle and I was injecting fluid under a very basic pH 10 to 12 solution in order to make a zinc sulfide in the cave that I could later convert to a silver sulfide so that I could actually get an atomic signature out of it. But that's it. That's the isotopic signature of the petroleum sulfur. And that's where it falls on the plot, which is completely different than at Lost River Cave. And what that means is that this is apparently getting pulled down towards that petroleum end member, which is neat. But it gets weirder, because the gypsum in the cave that I sampled on a whim had an even more depleted isotopic signature, which is plotting way down here, which you can't even see on that plot. And so apparently these are related, more related at least than this one up here, the St. Louis anhydrite. So how could that happen? Well, it actually all goes back to the chemistry. And when you look at it this way, it's really easy, because the petroleum seep has hydrogen sulfide that you can smell and I can sample. And that hydrogen sulfide reacts with oxygen to form sulfuric acid. And that sulfuric acid gets into the water, gets into the air, touches limestone, and makes gypsum, which I also sampled. And so that's really cool. But how important is that process? This is the result of a horrible linear algebra matrix that now just looks like squiggly lines, but I did the math for you. And this is how much sulfur is coming out of the petroleum seeps at any given point in the year at Blue Spring Caverns, where I had data for it. And on the bottom is how much is coming out of the rain, theoretically. And that's a mathematical model. And what you'll notice here at first is that it looks like there's too much coming out of the rain, because there should be this basically the same amount of sulfur in the rain at any of these sites. And so within scientific error, that's all in the same range, but this is too high. So I adjusted the model to bring this down. And what I adjusted with it was a 10 per mil isotopic shift in the sulfur signature of the end member that I was using for the petroleum, blah, blah, blah. But what that means is, instead of using that -14 number that I got out of the seeps, I used a -4. And you would think that that means I'm cheating, but actually it's the bacteria that cheat, because there's a published value for that process where the bacteria eat hydrogen sulfide, where they spit it out heavier than it came out. And actually that paper says they spit it out 12.5 per mil heavier. So this is a fair back of the envelope calculation, and it lines up much better. And when you look at what that means, it means that during dry season, more than half of the sulfur in the cave is coming from those petroleum seeps, which is a lot. And more to the point, it's rising up from below and making gypsum by dissolving limestone. And that would be a hypogenic process. But Art Palmer said that Blue Spring Caverns formed from rainwater dissolution and floodwater diversion, which is an epigenetic process. And he was right, because those things really are happening, and his work is very good. So the question is, how can both of those things be happening at the same time? And I say, I don't see why they couldn't. But the problem is that we're trying to call it epigenetic or hypogenetic when we could just call it something else. So I say, instead of saying Blue Spring Caverns is an epigenetic cave, we should all be saying it's a polygenetic cave, because clearly both of these processes were involved. And these are just kind of some jotted down ideas on how that might have happened. You have that petroleum brine forming before you had a cave there, when it was just fractures that had to be dissolved open into a cave. That petroleum brine was migrating and it had sulfur in it. And that sulfuric acid, when it was formed, is more caustic than the carbonic acid. So it's enlarging those fractures faster than the carbonic acid can. And that means it's really important. But then at some point, you hit a threshold where the fractures get big enough that the carbonic acid is moving faster through it than the sulfuric acid can, because there's just less of it. And then epigenetic processes are dominating. And that's why Blue Spring Caverns looks like an epigenetic cave when you look at it through morphology and hydrology. But when you look at it geochemically, it has the signature of an epigenetic cave or a hypogenetic cave. And so that was what I did my thesis on. And now we can look at some fun caving stuff. This is, yes.
The gypsum formations,
Mhm.
are they more prevalent? I mean, do they form more as well as
So
as much?
they,
The more acid, sulfuric acid,
yes.
the more gypsum you get.
So the answer is complicated because the gypsum also dissolves. So there's not a lot of gypsum in Blue Spring Caverns because mostly it's flushed out by the river, right? So it dissolves away. And the gypsum that I found was in a dry passage above. But the answer to your question, I think, is yes, that hypogenetic process brings sulfur in. So you can create more sulfur through, you can create more gypsum through that process because you have a source of sulfur. Whereas like in Mammoth Cave, and Lee, please correct me if I'm wrong from the back, but in Mammoth Cave, there were some papers showing that the gypsum in Mammoth Cave appears to be coming in from meteoric sulfur diffusing through the air and through the rain. And so it can form, but there's also a lot less of gypsum in Mammoth Cave than there is in like Carlsbad. And in Carlsbad, you just have a ton of that hypogenic sulfur gas that bubbled up and formed the cave very quickly. Go ahead. You're going to correct me. He's moving forward. Yeah.
Blue Springs is over 20 miles long.
Mhm.
These petroleum sheets is this in a small part of the cave?
Yes.
Scattered throughout.
They are right here in that red box. Thank you for asking. Yeah, they're right there.
Where do you take this water samples from?
So I took the water samples from the boat dock, which I'm going to get this. It's right about there, right? So there's a pretty good gap in between. And so that's why at the boat dock, we didn't see any hydrogen sulfide. It had all converted to sulfate at that point. But when we took a water sample at the seeps, there was hydrogen sulfide in it because it's so volatile.
So is this petroleum seeps that common in other Indiana caves?
I have no idea. I would like you all to tell me.
How do you identify it besides mentioning like black drill?
Yeah, so it's I have it smells like rotten eggs, right? The sulfur smell. But there's crude product there. Like it's not a rock. There's actually like bitumen. You can get it on your finger and it's black. Yeah, it's gooey. And then that white haze around it. If you see the white haze, that's bacteria. And that's bacterial activity. And they have to be eating something to do that. Does that make sense? If you ever see this, please let me know, because Blue Spring Caverns, I'm going to talk about, go through pretty quickly, just some slides from the Kentucky cave work that Lee and I do, where we have really big ones. But Blue Spring is the only time I've seen it in Indiana. But I feel pretty comfortable that there must be other places where that's happened. In Indiana.
Well, no, not
Okay.
Tennessee.
I've heard of that. I've not been there. Yes, that I would love to see that. I know there are some folks doing biology work in there. You should show me pictures. I'd love to see. Good. Go
I
ahead.
could jump in here for a second. Tim Hornaday. Kevin's
Oh, I'm
talking-
sorry. Tim is talking in my ear. Can we take Tim's question? I'll repeat it for you and then I'll take your question, Kevin. Is that okay? You can't hear him. I'm sorry. What is
Oh.
it, Tim?
Just a comment. Kevin Strunk knows something about a tar seep in Harrison Crawford State Forest.
Tim says that Kevin Strunk knows about a tar seep in Harrison Crawford State Forest. Kevin Strunk. There's a tar seep in Harrison Crawford State Forest. I have seen it on a map. I've never been there.
Okay, well, there was talk over. So here's my question though about this before we, you sample at West Temple Falls in the rice pool?
Yes, at the Rise Pool.
And so then, and then one, you know, although you were sampling where the lines, why not the true lines?
Because we didn't have access. It's on private property.
So you didn't.
We didn't sample there, but also my impression is that the water comes from a different source because it's true Lost River. I don't think it has the same amount of deep sulfur input there, but also no one has done a thorough study because the access is harder to get. So I would love to do that.
I mean, the thing about true lines, like which is only what half a mile quarter of
Mhm.
is that we're actually similarly, they have similar depths.
Right.
You know, so they, you know, I think that would be interesting to see. And maybe contrast that with.
So,
Assuming what's kept the ball.
I agree.
Wasn't kept the ball ideally was 180 feet. It's a hell of a depth.
I think
You know,
I agree completely. The difficulty, and I talked to Chris Dick about this actually, because the difficulty is if you sample the true rise at the surface, you're getting water from Orangeville Rise coming downstream. And so it's diluted. And I was talking to Chris Dick because I would love to use his dive robot to get samples from the bottom of the rise. And he was into it, but until we can figure out a way to make it take water samples for me, I don't have a good way to do it. But you're right, it would be really cool.
because, you know, the depth would be like 180, 200 feet.
Yeah,
You
absolutely.
know, it's pretty significant.
Absolutely, I agree. Are there any other questions before I hop ahead? Okay. I promise it'll be fun. Meanwhile, in Kentucky. So I actually do most of my caving in Wayne County, Kentucky, which is 10 miles north of the Tennessee border. And this is the Edwards Mountain System. So I do my science in Indiana, but I do my caving in Kentucky. And this is a geologic map here. This is Edwards Mountain here, right, Lee? No, wrong one, this one here. This is Edwards Mountain here, under Lee's son's butt. And this, though, I will tell you, is Edwards Mountain here, where it says Edwards Mountain. And what you'll see about it is that there's a fault running through. And there's also a big cave in it, right there. Don't tell anyone. And so I managed the data for the Edwards Mountain project. And there's really one big cave in there, which is Spelungers. And then we have a bunch of surface leads. So this is Green Garter, Elimination Hole, Gomeldonsk, and there's down here is Low Cave, which is our spring cave lead. These are all vertical entrances. If this was all connected together, it would be the deepest cave in the state of Kentucky, which is really exciting and why we like to work on it, even though it's very difficult. This is Green Garter Pit. And it is very wet. That's a sinking stream and waterfall dumping into it. We set up a tarp so that we could dig on it some more. It's only 14 feet deep, but it takes all that water. And we have a pretty good idea of where that water goes inside the cave. Lots of water. Lots of water. It's a very wet dig. Yeah, it's definitely loud, and there is a lot of air. This is Elimination Hole, which is that lead further to the north. It's an 80-foot drop, but it is super tight. Although they made it bigger now, so I was the only one who had to do that, I guess. It's only 140 feet of mapped cave in there, but there's a dig lead that we can hear water sinking. There's a waterfall in the distance, and we just haven't gotten to it yet. It's a weird, it's a gut twister. So you're like, I mean, I'm not even on anything, but I'm twisted around a bunch of rocks. What's really impressive is that Lee did it, and he's bigger than me. This is Gameldonsk, which is the lead to the far, far north. And it's just really tight. Oh, that's not the video I thought it was, but that's a small child in Gameldonsk. So you can see how tight and terrible it is. Very, very small. But Spelungers is a big cave. And at the moment we have 5.8 miles of survey. We did about 1.5 miles last year. And then things slowed down a lot. This is one of the dry upper passages. It is 320 feet deep, but like I mentioned, if we got all those leads connected together, it would be closer to 500 feet deep. And it is on Edwards Mountain, and it is along that fault. And there are places in this cave where you can put your hand on either side of the wall and there's slick and sides under it, and you are walking through the fault plane. And this is the profile of it. So this is the entrance drop. It's a 200-foot drop with a rebelay in it. And then there are several other ropes that you go down. This is the monsoon room where water, we know this is warped because these aren't very far apart, but Green Garter is to the north and the east of the lead. Water comes in here and goes down there. And that's elimination hole, which is above another one of these canyon pit complexes. And these are petroleum seeps. And this is on the crest of an anticline, which is a classic oil trap, and it's a fault line. And I saw these before I ever saw those petroleum seeps in Blue Spring Caverns, because the world is a funny place. This is a sulfur seep, we were calling them at the time, on the surface. And this has so much hydrogen sulfide coming out of it that I vomited here after this photo because it was disgusting and bad. This is another one of those petroleum seeps. And this is crude oil in my footprint because I took a step, came back 2 weeks later, and my footprint filled with oil. This is an up close picture taken by a really good photographer of one of those petroleum seeps. In Blue Spring Caverns, the petroleum seeps are about 1 foot long. In Spelunger's cave, they're about 20 feet long. So they're really quite big. And my impression is that the ones in Tennessee are similarly big. And you can see that you can see the filaments of the bacterial mounds. There's so much. This is where they live. And they're just eating that oil, and it's just letting out sulfur. And from my work in Blue Spring Caverns, it's likely that this is part of why this cave is there. And this is just another shot of that. This is me standing in the distance, and it's a petroleum seep from where I'm standing to the photographer, which again is about 20 feet. And it's just really quite striking. So I wanted to share that with you. That's where we do our fun work. We don't do the science there because I work for the Indiana survey, but if anyone would like to come map caves and it's vertical, let us know, because we have fun leads and fun things to do. Thanks for listening. That's all.
Is there any relationship with the French lick and those nasty sulfurs?
That is a really good question. And I am trying to look into that right now. We are drilling in French Lick. So right now we're doing geologic mapping in the Bedford Quad, which is basically from just south of Sullivan's Cave down to French Lick. And we're trying to do drilling in that valley so that I can get a core, because I think that it is. But Noel Crothy said that that sulfur was coming from the St. Louis gypsum. But I disagree, because this sulfur isotope signature is so different and there's so much of it. I don't think that there's enough. I think it has to be coming from some sort of gas or petroleum source. So I think so.
Like they have sulfur. I thought they had like hot springs or sulfur baths stuff.
I had not heard that. If you know, let me know.
There's a county park that used to have a big natural pool.
Well, and it's also true that a lot of these things have gone away. So are there caves in Indiana that have this? I think that there may have been more in the past, but we pumped the shallow petroleum reservoirs in Indiana dry and throughout the rest of the Midwest, right? So the Leesville Anticline, which is pretty close to Blue Spring Caverns, was pumped dry for oil in the 1950s. before that happened, there would have been more oil and more oil pressure and probably more oil in Blue Spring Caverns. So
Are you only interested in actively seeping?
I'm interested in all of it.
Someone else was talking, said they know some places for residue for all the volatile chemicals.
Yeah, I would love to see that in Indiana.
Yeah.
Very cool. I can let you all wrap up your meeting if you want, and then anyone who wants to talk to me about petroleum seeps and caves, I am super excited about it.
We can go talk at the slippery net.
We could, if my carpool would like to. We'll see.
Any other questions?
I will hand you back your phone. You are welcome.
Very nice. Okay, so thanks all. We'll go ahead and wrap up next meeting. Remember, first Wednesday, December. We'll see you all then. Next point.
Thank you. See you guys.
See you all later.
Got cash. You want to give her 50 or 40? Okay. Okay. Uh-oh. Goodbye, everybody. See you next time. We're gonna try to do Dean's thing again next month, I think.
It's very much.